Chapter 4. Recurrent Neural Networks, RNNs, and Variants. 4.1 Fundamentals of RNNs. Recurrent neural networks, RNNs, are a special class of artificial neural networks designed to recognize patterns in sequences of data, such as text, genomes, handwriting, the spoken word, or numerical time series data emanating from sensors, stocks, and many other sources. Unlike feed-forward neural networks like convolutional neural networks, CNNs, RNNs possess a unique feature. They have a form of memory that captures information about what has been calculated so far. In essence, they maintain a state that can theoretically hold information about all previous computations. This characteristic allows them to exhibit dynamic temporal behavior for a time sequence. This makes them extremely powerful for tasks involving sequential data, such as natural language processing, NLP, speech recognition, and language translation. The fundamental building block of an RNN is a unit that repeats across the sequence of the input data. At each sequence step, the RNN unit takes two inputs, the current time step's data and the hidden state from the previous time step. The hidden state serves as the network's memory, carrying forward information computed in prior processing steps. The process is essentially a loop where, at each step, the output of the loop is influenced by the previous computations. When the data sequence is fed through the RNN, each step's output depends not only on its current input, but also on a recursive function of past inputs. The recurrent nature of RNNs makes them suitable for handling variable-length sequence input, a common trait in natural languages. For example, when predicting the next word in a sentence, it's not the length of the sentence that matters but the context provided by the preceding words. RNNs can, in theory, use their internal memory to process arbitrary sequences of inputs. This makes them applicable in a wide variety of tasks, not just those related to text or speech. Any domain where the sequence of data points is crucial, such as video frame analysis, weather forecasting, or stock market trends, can potentially benefit from the sequence modeling capabilities of RNNs. However, one major problem with RNNs is the difficulty they have in learning long-range dependencies. In principle, RNNs can maintain information in their hidden state for long periods. In practice, when training RNNs, the gradient of the loss function used to update weights can vanish or explode, making it challenging to retain the influence of earlier inputs, known as the vanishing and exploding gradient problems, respectively. This issue largely stems from the repetitive multiplication of gradients through each time step in the backpropagation through time (BPTT) algorithm, which is used to train RNNs. If the gradient is small, it shrinks exponentially as it backpropagates, and if it is large, it grows exponentially. To mitigate the vanishing gradient problem, refined versions of RNNs have been developed, most notably long short-term memory (LSTM) networks and gated recurrent units (GRUs). LSTMs introduce a memory cell that can maintain its state over time, and operations that regulate the flow of information into and out of the cell, effectively allowing it to retain information for longer periods. This is achieved through a sophisticated mechanism composed of gates, specifically the forget gate, input gate, and output gate. Each gate in the LSTM can learn what information is relevant to keep or discard during training. Similarly, GRUs simplify the gating mechanism and combine the forget and input gates into a single update gate. These architectures have proven to be more effective at capturing long-term dependencies because they are explicitly designed to address the shortcomings of traditional RNNs. RNNs are trained using a variant of the backpropagation algorithm called backpropagation through time (BPTT). In BPTT, errors are propagated backward through each time step of the network. Weights are then adjusted to minimize the loss function. Because RNNs share parameters across all time steps, the weight updates at each step are dependent not only on the errors of the current step, but also on the network's performance on previous steps. This sharing of parameters is intended to generalize the learning across the sequence, but it also means that the RNN needs to be able to manage errors that could propagate from any point in the sequence, thus making learning from earlier time steps increasingly difficult as the sequence gets longer. The capacity of RNNs to model complex sequences comes with the cost of computational intensity. As the sequences get longer and the network architecture gets more complex, training times can become significantly longer compared to other neural network architectures. This is because each RNN cell's hidden state depends on the previous cell's output, which creates a sequential dependency that prevents parallelization within sequences during training. To address these challenges, researchers have proposed various optimization strategies, including truncated BPTT, where the sequence is divided into smaller subsequences, and gradient clipping, which involves capping the gradients to prevent them from exploding. In addition to LSTM and GRU, several other variants of RNNs have been developed to tackle specific problems in sequence modeling. Bidirectional RNNs, for example, process data in both directions, forward and backward, to capture context from both sides of a sequence point for improved accuracy on certain tasks. Attention mechanisms, often coupled with RNNs, allow the network to focus on specific parts of the sequence when generating an output, which is particularly useful in tasks like machine translation. Using RNNs effectively necessitates a careful consideration of their architecture and the specific requirements of the task at hand. Pre-processing steps, like normalizing input data and encoding categorical variables, are critical to providing data in a format the RNN can work with effectively. Selecting the right optimizer and tuning its parameters are also crucial to ensure stable and efficient training. Consequently, despite the theoretical allure of RNNs for sequence modeling, practical implementation requires meticulous planning and extensive experimentation. In various application domains, RNNs have demonstrated their ability to outperform other models at sequential data tasks. Their inherent design allows them to create a refined understanding of sequence context, which is not achievable by models that treat each input independently. However, this capability also demands diligent handling of the challenges that RNNs present, notably the tendency towards overfitting, vanishing and exploding gradients, and their intensive computation requirements. To effectively leverage the potential of RNNs, it is essential to balance these considerations with an overarching goal of accurate sequence representation and prediction. With their profound impact on fields like natural language processing and speech recognition, RNNs represent a considerable advancement in the capabilities of neural networks to process sequences of information. As we push forward the boundaries of what is computationally feasible and develop further insights into sequence modeling, we can expect RNNs and their variants to play a pivotal role in the evolution of artificial intelligence. Their adaptability across different data types and the continual refinements in their architecture ensure that RNNs will continue to be a central topic of research and application in the neural network community. 4.2 Challenges with vanilla RNNs, vanishing and exploding gradients. Recurrent neural networks, RNNs, are powerful tools in the arsenal of machine learning techniques, designed particularly to handle sequential data. Unlike their feed-forward counterparts that assume independence between inputs, RNNs maintain internal states that capture temporal dependencies in the data. However, despite their theoretical promise, RNNs face several practical challenges. One of the most notable issues is the vanishing and exploding gradients problem, which we will explore in this section. The vanishing gradients problem occurs during the training process. RNNs are trained using a method called backpropagation through time, BPTT, which involves unrolling the network over time and calculating gradients of a loss function concerning the weights, updating the network's weights accordingly. During this backpropagation, gradients are computed for each time step, and these values are multiplied as they propagate backward through the network. When the gradients of these values are small, less than 1, they tend to get smaller and smaller with each time step. This results in the gradients vanishing as the error is backpropagated through the network, leading to very little or no learning signal for the early layers. This makes it difficult for the RNN to learn long-term dependencies within the input data, severely limiting their capacity to deal with longer sequence tasks. Conversely, the exploding gradients problem can occur when the gradients assume too large values. During the BPTT, large gradients can exponentially grow as they are backpropagated through each time step. When this happens, the model's weights can receive extremely large updates, causing the learning process to become unstable. This instability may lead to the weights diverging instead of converging to a set of values that minimizes the loss function, making the network untrainable. Why do vanishing and exploding gradients occur? They are fundamentally caused by the nature of the computations involved in RNNs and the use of nonlinear activation functions like tanh and sigmoid. These activation functions have derivatives that are less than 1 for all inputs, meaning that when backpropagation involves multiple layers over many time steps, the gradients can reduce exponentially. This recurrent multiplication can lead to vanishing gradients if the activation functions or initial weights are such that the derivatives multiplications diminish the gradient, or exploding gradients if the multiplications increase the gradient. The initial weights of RNNs also play a critical role in the prevalence of the vanishing and exploding gradient problems. Poor initialization of these weights can exacerbate the issue by making it more likely that the gradients will vanish or explode. If initial weights are set too small, vanishing gradients are more prevalent. If they are set too large, exploding gradients become the concern. It's a delicate balance that requires careful consideration during the design of the network. Furthermore, the structure of an RNN exacerbates the vanishing gradient problem. Since the same weights are used at each time step during the recurrent process, the gradients are more prone to diminishing or increasing rapidly. This repeated multiplication of gradients of less than 1 for vanishing gradients has a compound effect over many time steps, leading to the gradients approaching 0. Several methods have been proposed to address these problems, with varying degrees of success. One widely utilized solution to the vanishing gradient problem is the introduction of gated structures, such as long short-term memory, LSTM units, or gated recurrent units, GRU, which include mechanisms to remember and forget information selectively. These architectures enable the network to maintain a more constant error flow through time, mitigating the issue of vanishing gradients by ensuring that the gradient neither vanishes nor explodes as it is backpropagated through time. Gradient clipping is a technique commonly used to counteract exploding gradients. This technique involves setting a threshold value, and if the gradients exceed this threshold, they are scaled down to keep the values within a manageable range. This prevents the updates during training from becoming too large and destabilizing the model, but it does not address the underlying causes of the problem. Another approach to tackle these issues is by using different activation functions, such as the rectified linear unit, ReLU, which does not saturate in the positive domain and thus can mitigate the vanishing gradient problem to some extent. However, care must be taken, as ReLU can also be susceptible to the exploding gradient problem and might lead to dead neurons, neurons that consistently output a zero gradient. Initialization strategies, such as Xavier or He initialization, can also help to tackle the issues of vanishing and exploding gradients. These methods set the initial weights of the network in a manner that takes into account the size of the previous layer, aiming to keep the variance of the outputs from each neuron consistent across layers. Such strategies lead to a more stable distribution of gradients, thereby improving the capacity to learn from data. Some researchers have also explored the use of residual connections in RNNs, similar to those used in ResNet architectures for convolutional neural networks. These connections create an alternative pathway for the gradient to flow through, potentially skipping over layers where it might otherwise vanish or explode. By providing this shortcut route, gradients can bypass the repeated multiplications through the problematic layers, alleviating the vanishing gradient problem without fundamentally changing the network's learning capability. Finally, the understanding and mitigation of vanishing and exploding gradients remain active areas of research in deep learning. Despite the practical solutions mentioned herein, developing and refining techniques that allow RNNs to learn effectively without succumbing to these issues is an ongoing challenge. Researchers continue to propose innovative models and training methods to enable the stable and robust learning of temporal dependencies over various lengths and complexities. 4.3 Long Short-Term Memory Networks, LSTMs. Long Short-Term Memory Networks, LSTMs, are a type of recurrent neural networks, RNNs, that have been designed to address some of the limitations found in traditional RNNs. The main issue with basic RNNs is the vanishing gradient problem, which makes learning on long sequences particularly challenging. As the sequence gets longer, the gradients which are backpropagated can vanish or explode, making it difficult for the RNN to learn dependencies between events that are far apart in time. LSTMs tackle this problem through a unique architecture that allows them to better capture long-range dependencies. The architecture of an LSTM unit is comprised of a cell state and 3 gates, an input gate, an output gate, and a forget gate. The cell state acts as a conveyor belt of sorts. It runs straight down the entire chain of LSTM units with only minor linear interactions, allowing it to transfer information easily across the network without changes. This is what enables LSTMs to maintain information over long periods, as the cell state has the capability to add or remove information, regulated by the gates. Each gate within an LSTM has a specific function. The input gate controls the extent to which a new value flows into the cell state. The output gate controls the extent to which the value in the cell state is used to compute the output activation of the LSTM unit. The forget gate, perhaps the most critical component of the LSTM, allows the cell to remove information that is no longer considered relevant to the LSTM's task. These gates are composed of a sigmoid neural net layer and a pointwise multiplication operation. The forget gate uses the sigmoid function to output numbers between 0 and 1. A value of 0 indicates that the LSTM should completely forget the corresponding information, whereas a value of 1 indicates that it should remember it entirely. This acts much like a relevance filter for the LSTM cell, learning what to keep from prior steps and what to discard. The input and output gates function in a similar selective manner, modulating the flow of new data into the cell and out to the next layer respectively. Training LSTMs involves backpropagation through time, BPTT, similar to other RNNs. However, due to their gated structure, LSTMs are able to preserve gradients and thus have the opportunity to learn from longer sequences. BPTT unfolds the LSTM over a sequence of time steps and computes the gradients over these time steps in reverse order, updating the network weights according to these computed gradients to minimize the loss function. Despite their advantages, LSTMs are not without challenges. They can be computationally expensive due to their complex structure. They also have a large number of parameters arising from 3 different gates and the cell state, which may increase the training time and require more data to learn effectively. Furthermore, finding the optimal configuration of an LSTM for a specific task can be a time-consuming process involving much trial and error in tuning hyperparameters, such as the number of LSTM units and the learning rate. A common variant of LSTMs is the gated recurrent units, GRUs. GRUs modify the LSTM architecture by combining the input and forget gates into a single update gate and merging the cell state and hidden state. By doing so, they simplify the LSTM model and can reduce the computational work required while still retaining a similar performance level to standard LSTMs on many tasks. Whether to use LSTM or GRU often depends on the specific requirements of the application and the computational resources available. The applications of LSTMs are diverse and span many fields, including natural language processing, NLP, speech recognition, and time series prediction. In NLP, for example, LSTMs have been successfully applied to tasks such as language modeling and machine translation. They are capable of capturing the syntax and semantics of a language over long stretches of text, making them highly effective in understanding and generating human language. In time series prediction, LSTMs can be used to predict future values based on historical data. This is of particular use in areas such as stock market prediction, weather forecasting, and industrial process control. Their ability to remember past inputs for an indefinite amount of time makes them suitable tools for these kinds of tasks, where past information can be crucial for making accurate predictions. Finally, while LSTMs have been a powerful tool in the advancement of deep learning, they are also constantly evolving. Researchers continue to propose modifications to improve their performance or to adapt them for new kinds of data and tasks. Techniques such as bidirectional LSTMs, which involve processing data in both forward and backward directions, and attention mechanisms, which allow LSTMs to focus on different parts of the input sequence, are examples of how LSTMs are being extended to enhance their capabilities. The evolution of LSTM architectures is indicative of the rapidly advancing field of machine learning. As computational capabilities increase and new theoretical insights are gained, LSTM networks will continue to evolve. However, the current form of LSTMs already represents a significant milestone in the development of neural networks, offering a robust model for learning from sequential data that has had a widespread and profound impact on the field. Their continued use and development are expected, as they remain central to the toolkit of machine learning practitioners facing problems involving sequential data. 4.4 Gated Recurrent Units, GRUs. Gated Recurrent Units, GRUs, are a variant of recurrent neural networks, RNNs, introduced as a solution to the vanishing gradient problem inherent in standard RNNs. The vanishing gradient problem occurs during backpropagation through time when gradients of the loss function become increasingly small, causing the weights of the early layers in the network to receive very little update, if any. This makes it challenging for the standard RNN to learn long-term dependencies within the data. GRUs employ gating mechanisms to control the flow of information, addressing this issue and enabling the network to better capture dependencies for sequences of varying lengths. A GRU modifies the RNN architecture by introducing two gates, the update gate and the reset gate, which regulate the flow of information inside the unit. The update gate helps the model determine the amount of past information from previous time steps that needs to be passed along to the future. This is crucial for the network to retain relevant information over long sequences without being overwhelmed by unnecessary data. Conversely, the reset gate decides how much past information to forget, aiding the GRU in dropping irrelevant or noisy data that could adversely affect the current step's computation. The structure of a GRU allows for each unit to effectively capture dependencies for a particular range of sequence lengths due to its learnable gates. Mathematically, the update gate is represented as a sigmoid function that outputs values between 0 and 1. A value closer to 0 signifies that less of the past information is necessary, while a value closer to 1 indicates the importance of retaining this information. The reset gate also outputs values in the same range, where a value near 0 signals it's appropriate to discard previous computation, and a value near 1 means to maintain the computation for further usage. One of the key advantages of GRUs over standard RNNs is their ability to mitigate the risk of overfitting on shorter sequences. This is especially helpful when dealing with datasets containing a diverse range of sequence lengths. Because GRUs are adept at learning which information to keep or discard, they can prevent irrelevant features from earlier in the sequence from influencing the output, which can enhance generalization and performance on unseen data. When the data involves complex sequences where certain segments hold more importance for prediction than others, GRUs can also provide better results than RNNs. The gating mechanisms enable the GRU to give varying weights to different parts of the sequence, making it more adaptable to the data's structure. This ability to learn which parts of the sequence are important is a critical property because it enables the model to focus on the most predictive features. In a GRU, each gate has its own set of weights and biases, which are learned during the training process. By updating these parameters, the network learns the optimal strategy for processing sequences, improving its performance on tasks such as language modeling, speech recognition, and time series prediction. The GRU architecture provides a flexible framework that is suitable for a wide range of sequence learning tasks, thanks to its dynamic gating mechanisms. The training process for a GRU involves iterative adjustment of its weights through backpropagation through time, BPTT, similarly to how standard RNNs are trained. However, because GRUs mitigate the vanishing gradient problem to some degree, they often require fewer training iterations to converge to a good solution. This can lead to a reduction in training times and faster deployment of models, especially when compared to traditional RNNs or even other sequence learning models, such as long short-term memory networks, LSTMs. In practice, GRUs and their gating mechanisms tend to have less computational complexity than LSTMs. While LSTMs have 3 gates, input, output, and forget gates, compared to the GRUs 2, this distinction can result in more efficient computations in GRUs under certain circumstances. For example, with datasets where the time-related dependencies are not extremely long or when computational resources are limited, GRUs often offer a favorable balance between computational efficiency and model performance. It is important to note that GRUs are not universally superior to LSTMs or vice versa. The effectiveness of each model depends on the specific application and dataset. Some tasks may benefit from the greater complexity and expressiveness of LSTMs, while others can be addressed more efficiently with the simpler GRU architecture. Researchers and practitioners must experiment and conduct thorough evaluations to determine which model is the best fit for their particular use case. Finally, GRUs serve as a robust tool within the deep learning practitioner's toolkit, offering a valuable approach for dealing with sequential data. Their design enables effective information flow through time, making them suitable for a diverse array of applications where sequence learning is crucial. As research continues to evolve in the field of deep learning, GRUs, alongside RNNs and LSTMs, remain key components in the ongoing effort to model temporal dynamics and sequential dependencies within data. 4.5 Bidirectional RNNs and Deep RNNs. Bidirectional recurrent neural networks, BRNNs, extend the conventional RNN framework by providing the network with information from both past and future states. Unlike standard RNNs which process data in a single direction from the first input to the last, BRNNs consist of 2 separate RNNs, the forward and backward RNNs, that are trained simultaneously. The forward RNN traverses the sequence from start to end, while the backward RNN covers the sequence from end to start. Both networks are connected to the same output layer, which ensures that the output at each time step is determined by the immediate past as well as the future. The architecture of a typical BRNN allows it to capture context in both directions, which makes them particularly useful in applications where the context of the input is crucial. For instance, in natural language processing tasks like sentiment analysis or language translation, the meaning of a word can depend heavily on the preceding and succeeding words. In such cases, BRNNs outperform their unidirectional counterparts by leveraging the complete context, thus producing a more accurate representation of the sequence data. A significant challenge with BRNNs, much like with conventional RNNs, is the learning of long-range dependencies. When the sequences are long, BRNNs can struggle with retaining information from the early or latter parts of the sequence. This is due to the vanishing gradient problem, an issue where the gradient of the loss function decreases exponentially with the length of the sequence, making it particularly arduous to update the weights of the early layers during the backpropagation phase. Consequently, both the forward and backward passes of a BRNN may not effectively capture the influences of distant elements within a sequence. The application of gated recurrent units, GRUs, and long short-term memory units, LSTMs, within BRNN architectures can help mitigate the vanishing gradient problem. Both GRUs and LSTMs introduce gating mechanisms that regulate the flow of information through the network, allowing them to maintain a memory over longer sequences. When employed in a bidirectional setting, these gated variants can process sequences more effectively, as they combine the benefits of context gathering from both directions with the robustness of GRUs and LSTMs in handling long-range dependencies. Deep RNNs are another extension to the typical RNN architecture, which involves stacking multiple hidden layers on top of each other, forming a deep network. Each layer in a deep RNN captures different levels of abstraction of the input data, thereby enriching the network's ability to learn complex patterns. Such hierarchical representation is useful in many tasks where the data contains intricate structures that a single layer may not adequately capture. Learning abstract representations at each level allows deep RNNs to construct more powerful predictive models. Deep RNNs, however, come with the burden of increased computational complexity and the risk of overfitting, especially as the number of parameters grows substantially with each added layer. To address these challenges, techniques such as dropout, regularization, and appropriate initialization are generally adopted. Dropout is particularly effective, as it can reduce overfitting by randomly omitting a subset of features or activations within hidden layers at each training step, thereby forcing the model to learn redundant representations that are robust to the loss of any individual representation. Integration of deep learning techniques into RNNs, including deep BRNNs, becomes even more valuable when accounting for the varying types of information in the input sequences. In particular, convolutional neural networks, CNNs, can be combined with RNNs to handle sequential inputs that have spatial relationships, such as video frames. In this case, CNNs are utilized to extract spatial features which can then be processed temporally by the RNN layers. Such integrations allow for what is referred to as convolutional RNNs and are crucial in harnessing the advantages of both convolutional and recurrent structures. Training deep RNNs requires careful handling of the temporal dependencies present in the data. Particularly pertinent is the backpropagation through time (BPTT) algorithm, which unfolds the RNN across time steps to create a deep network, treating each time step's output as a layer's output in a feed-forward network. BPTT demands considerable computational resources, both in terms of memory and processing power, as gradients need to be computed and stored across all time steps. Efficient implementations and parallel computing are often used to make training deep RNNs feasible. A notable aspect of training deep RNNs is the strategy of using truncated backpropagation through time. In this approach, rather than backpropagating through the entire sequence, the sequence is divided into shorter segments, and the network is updated based purely on these segments. Truncating the sequence in this manner helps to make the optimization more manageable and allows for faster convergence, since it reduces the computational load and mitigates the vanishing gradient problem by shortening the path that the gradients must flow through. Hybrid models that combine BRNNs with deep learning techniques such as deep feed-forward neural networks provide a potent architecture for modeling complex sequential data. The deep layers can learn sophisticated feature hierarchies from the data, while the bidirectional layers ensure that the temporal context is fully exploited. By doing so, they become robust to variations within the sequence data and improve the predictive performance across a myriad of tasks from varying fields, including speech recognition, time series prediction, and bioinformatics. The sophistication of BRNNs and deep RNNs requires a significant amount of data to train effectively. In the absence of large-scale datasets, transfer learning and unsupervised pre-training techniques can be adopted. Transfer learning involves training a model on a large dataset and then fine-tuning it on a smaller, task-specific dataset. Unsupervised pre-training, on the other hand, involves training the network to learn a good feature representation of the data without using labeled examples, often by reconstructing the input sequence. These techniques help improve the performance of the model when training data is limited. The advancements in BRNNs and deep RNN architectures continue to push the boundaries of what is possible in terms of sequence modeling. However, the progress is not without challenges. Further research and development are needed to optimize these network structures, improve their training efficiency, and effectively handle the complex interdependencies within varied sequence data. As we continue to enhance these models, they will undoubtedly become even more integral to complex sequential data analysis and prediction across diverse domains. 4.6 RNNs for natural language processing. Natural language processing, NLP, stands at the forefront of the push for artificial intelligence to interpret, generate, and ultimately understand human language. Traditional neural networks, while adept at handling structured data, fall short when dealing with sequential data where timing and the order of data points are critical. Recurrent neural networks, RNNs, address this gap by incorporating a feedback loop, enabling the network to maintain a form of memory. In NLP tasks, this memory is essential as it allows the model to take into account previous words in a sentence, effectively understanding context and maintaining coherence in language processing tasks. RNNs retain information from previous inputs by looping output back into the network, fundamentally different from feed-forward networks. This looped structure simulates a sequence of decisions influenced by preceding elements. In language, each word's meaning may change with respect to the words that come before. For example, in the sentence, "He lifted the trunk," understanding what trunk refers to depends on the context provided by previous words. In a feed-forward network, each input would be independent, stripping the ability to discern that trunk could refer to a large box or the main woody stem of a tree, while an RNN can retain the sequential context. However, RNNs are also known to struggle with long-term dependencies due to the issue of vanishing gradients, where the gradients used in updating network weights become increasingly smaller as they are propagated back through each time step. When processing long sentences or documents, the network might fail to carry relevant information from the beginning to the end of the sequence, leading to poor performance. This challenge becomes pronounced in complex NLP tasks, such as language translation, where sentences can span several clauses and require understanding from start to finish. To mitigate the problem of vanishing gradients, long short-term memory (LSTM) networks, a special kind of RNN, were introduced. LSTM networks incorporate gate mechanisms: the input gate, forget gate, and output gate. These gates determine what information should be kept or discarded at a given time step, and are trained to learn long-term dependencies, which makes them more effective for NLP tasks that involve larger contexts. LSTMs have a cell state that travels across time steps with minimal changes, carrying relevant information throughout the sequence, which is critical for tasks like text summarization or sentiment analysis. Another variant of RNNs, the gated recurrent unit (GRU), simplifies the LSTM architecture by combining the input and forget gates into a single update gate and merging the cell state with the hidden state. This reduced complexity can lead to faster training times and less data overfitting, albeit with the trade-off of potentially reduced capacity to model extremely complex patterns. GRUs have proven effective in NLP tasks where the computational budget is limited, or the sequence lengths are moderate, making it a favorite for tasks like conversation modeling. Training RNNs on NLP tasks typically requires large amounts of labeled text data. In language modeling, for instance, the network is trained to predict the next word in a sequence, giving it the ability to generate text. To do this effectively, the RNN needs to learn the structure of the language, including grammar and semantics. This process can be computationally intense and slow, demanding optimization techniques like truncated backpropagation through time, BPTT, which limits the number of time steps over which gradients are computed, to manage computational resources effectively. Attention mechanisms have also been introduced in RNN architectures to improve performance on NLP tasks. The attention model allows the network to focus on different parts of the input sequence when performing a particular task, which is beneficial when processing long sequences where certain segments are more relevant than others. For example, in machine translation, attention allows the network to focus on specific portions of the source text when translating to the target language. This results in improved translation quality and the ability to handle sentences with complex structures. Despite the advances provided by LSTMs, GRUs, and attention mechanisms, RNNs can still be challenging to train effectively. Several methods have been proposed to address these challenges. One of them is teacher forcing during training, where the predicted output from a previous time step is replaced with the actual observed output. This can accelerate learning by pushing the network towards the correct structure of the data, but might also cause issues if the network overly relies on this method, a phenomenon known as exposure bias. Embeddings play a crucial role in preparing textual data for RNN-based NLP tasks. Word embeddings such as word tuvec or glove provide dense representations where semantically similar words are mapped to similar points in vector space. The usage of embeddings allows RNNs to work with efficient, continuous representations of words rather than sparse, one-hot encoded vectors. This not only improves the quality of the language features learned by the network, but also reduces computational overhead. In practical NLP applications, RNNs and their variants have found wide usage. Chatbots, translation services, and predictive typing systems all leverage the sequential processing capabilities of RNNs to provide more accurate and context-aware interactions. These systems are continuously refined as the underlying models, training procedures, and linguistic data improve. As neural network research progresses, RNN-based solutions in NLP are expected to become even more sophisticated, handling the nuances and complexities of human language with greater finesse. The dynamic nature of language, with its idioms, evolving slang, and cultural references, represents an ongoing challenge for neural network models. But with each generation of RNNs and their variants, the gap between human and machine understanding of language grows narrower, opening up possibilities for more natural and effective human-computer interaction. 4.7 Sequence-to-sequence models. Sequence-to-sequence models, commonly referred to as seek-to-seek, are a class of architectures designed for tasks where both the input and output are sequential data. These models have proven especially effective in natural language processing (NLP) applications like language translation, text summarization, and chatbot development. The foundational concept of a seek-to-seek model involves two primary components, an encoder and a decoder, both of which are typically instantiated as recurrent neural networks (RNNs), although other architectures like long short-term memory (LSTM) networks or gated recurrent units (GRUs) can be employed. The encoder processes the input sequence in a step-by-step fashion and generates a context vector, also known as the hidden state. This context vector aims to encapsulate the relevant information from the input sequence that is necessary for generating the output. The quality of this context representation is critical, as it serves as the sole conduit of information from the encoder to the decoder. Because RNNs can have difficulty handling long-range dependencies due to issues like the vanishing gradient problem, LSTMs and GRUs, with their more complex internal gating mechanisms, are often favored in seek-to-seek models to maintain the integrity of information over longer sequences. Upon receiving the context vector, the decoder begins generating the output sequence, also in a stepwise manner. The decoder predicts each element of the output sequence conditioned on its previous predictions and the context vector. Since the decoder relies on past predictions to inform each subsequent step, errors can accumulate during this process, potentially reducing the model's overall performance. This emphasizes the importance of accuracy during the early stages of the output generation phase. Indeed, both the encoder and decoder components of seek-to-seek models are trained jointly to optimize performance, typically using a loss function that compares the predicted sequence to the true sequence. The training of seek-to-seek models is further complicated by the need for alignment between the input and the output sequences. This is not always a trivial task, since there isn't always a one-to-one correspondence between the elements of the input and output sequences. To address this, attention mechanisms were introduced, which allow the decoder to focus on different parts of the input sequence during each step of the output generation. The attention mechanism works by weighting the importance of each input as it relates to the output, effectively learning what to pay attention to as the context vector is utilized in generating the sequence. The incorporation of attention mechanisms has significantly improved the performance of seek-to-seek models, particularly in tasks like machine translation. In machine translation, for example, attention allows the model to focus on syntactical nuances and contextual cues within the input sentence that are crucial for producing a coherent translation. This means that in a translated sentence, the order of words and phrases in the target language can be influenced directly by words and phrases from anywhere in the source sentence, mirroring the way human translators often revisit different parts of the original text to better understand the meaning. In addition to attention mechanisms, another variant of seek-to-seek models, known as the transformer model, has risen in prominence. Transformers eschew recurrence altogether and instead rely solely on attention mechanisms to process sequences. By doing so, They allow for greater parallelization in training and overcome some of the computational inefficiencies intrinsic to RNNs. The transformer architecture has formed the backbone of several state-of-the-art models in NLP, underlining the progress and continuing evolution of seek-to-seek models. While seek-to-seek models and their variants have reshaped the landscape of sequence-based tasks in machine learning, they are not without limitations. One such limitation is the requirement for large amounts of training data to perform well. Seek-to-seek models are data-hungry, often necessitating extensive corpuses of annotated data for training. In the case of language translation, this means parallel corpuses of text, which are expensive and time-consuming to produce. This reliance on large datasets can also lead to models that inadvertently capture biases present in the training data, which can perpetuate and even amplify these biases in their outputs. Moreover, the problem of overfitting is especially pertinent in seek-to-seek models. Overfitting occurs when a model learns the training data too well, including its noise and outliers, causing it to perform poorly on unseen data. Regularization techniques, such as dropout, are employed to mitigate overfitting by randomly deactivating a subset of neurons during training, which encourages the model to generalize better to new data. However, finding the right balance that avoids both underfitting and overfitting remains a challenge. Finally, the interpretability of seek-to-seek models is often limited. Due to the complexity of these models, particularly those with attention mechanisms or transformer architectures, understanding how they make specific decisions can be difficult. This black box nature makes it challenging to troubleshoot errors or to provide explanations for the model's behavior, which is increasingly important in applications where transparency and accountability are required. Despite these challenges, seek-to-seek models continue to be a primary choice for handling sequence-based problems in machine learning. They have set new benchmarks in a diverse array of tasks, significantly advancing our ability to automate and improve upon complex language-based tasks. As research in this field progresses, further innovations and refinements in seek-to-seek architecture are expected, which will likely expand their capabilities and applicability. In the pursuit of models that can process sequences with human-like fluency and insight, seek-to-seek models have proven themselves indispensable tools in the machine learning toolkit. 4.8 Attention Mechanisms and Transformers. Understanding the traditional framework of recurrent neural networks, RNNs, is critical as a precursor to delving into advanced variants that include attention mechanisms and transformers. RNNs are potent tools in machine learning for handling sequential data, such as text, speech, and time series. By design, RNNs possess the capability to maintain information across sequences, achieved through loops within the network that pass information from one step of the sequence to the next. This recurrent structure allows the network to effectively remember previous inputs when processing current or future ones, which is instrumental for tasks that require context understanding, such as language processing. However, RNNs are not without drawbacks. The primary challenge they face is the issue of long-term dependencies. As the gap between relevant information increases, RNNs struggle to maintain the performance as gradients propagated back in time tend to either vanish or explode, a phenomenon known as the vanishing and exploding gradient problem. Several techniques, such as gradient clipping and gating mechanisms found in long short-term memory (LSTM) networks and gated recurrent units (GRUs), have been developed to mitigate these issues, resulting in more stable learning processes. The introduction of attention mechanisms marked a significant evolution in the field of neural networks, primarily addressing the deficiencies of RNNs in handling long sequences. The concept of attention enables models to focus on different parts of the input sequence dynamically, drawing parallels to how human attention works. It gives the model the capability to weigh the importance of different inputs differently, leading to improved handling of sequences where the relevant information might be widely dispersed. Attention mechanisms can be employed in conjunction with RNNs to enhance their performance, and they also serve as the foundational principle behind the development of transformers. Transformers, introduced in the seminal paper Attention is All You Need by Vaswani et al., leverage attention mechanisms to the fullest, eschewing recurrence altogether. These models use self-attention to weigh the significance of all parts of the input sequence simultaneously. This parallelization of the attention process allows transformers to be trained more efficiently than RNNs, particularly on large datasets. The transformer architecture is composed of an encoder to process the input sequence and a decoder to generate the output. The encoder consists of multiple layers, each containing self-attention and feed-forward neural network components, while the decoder has an additional component to pay attention to the encoder's output. The self-attention mechanism within transformers plays a critical role. At a high level, it operates by generating three sets of values from the input: queries, keys, and values. The attention function computes the dot products of the query with all keys, assigns weights to the values accordingly, and then outputs a weighted sum of values. This process enables the transformer to focus on different parts of the input sequence and draw global dependencies, regardless of their position in the sequence. Scaled dot product attention is the specific attention function used in transformers. It scales the dot products by the square root of the dimension of the key vectors, stabilizing the gradients during training as it prevents them from becoming too large. This attention function is computed simultaneously across multiple heads in what is called multi-head attention, allowing the model to capture different aspects of the input at different positions. This parallel attention mechanism lets transformers gather comprehensive context from the input sequence. Transformers also benefit from what is known as position encoding. Since the self-attention mechanism does not inherently account for the order of the sequence, positional encodings are added to give the model information about the position of the elements in the sequence. These encodings can be fixed or learned, and are added to the input embeddings at the base of the transformer model. This addition ensures that the transformer retains the ability to consider the order of the sequence, which is essential for tasks that require understanding the structure of the data, such as natural language processing. An impressive attribute of transformers is their transferability and the emergence of large pre-trained transformer models such as BERT, bidirectional encoder representations from transformers, and GPT, generative pre-trained transformer. These models are pre-trained on massive amounts of data and can be fine-tuned for specific tasks, which allows them to achieve state-of-the-art performance on a wide range of natural language processing tasks. Pre-trained transformers can understand context, infer meaning, and even generate coherent and contextually relevant text. The versatility of transformers extends beyond natural language processing. They have shown promise in other domains such as computer vision, where they can process images as sequences of patches and extract complex, high-level features. The emergence of vision transformers, VITs, underscores the potential scope of the transformer architecture beyond its initial application area. As the applications of transformers broaden, they continue to push the boundaries in various fields of artificial intelligence. One notable advancement brought about by transformers is their impact on the field of machine translation. The ability of transformers to consider the entirety of the input and output sequences has enhanced the quality of translation models, leading to systems that are closer to human parity in some language pairs. This proficiency is owed to the global attention and context understanding that transformers offer, which is critical in capturing the linguistic nuances necessary for accurate translation. With the advent of transformers, research continues to explore novel attention mechanisms and architectures. The evolving landscape of neural network research, driven by attention and transformers, presents a wealth of opportunities for advancement. As computational resources grow and algorithms become more sophisticated, we may witness the emergence of even more powerful attention-based models that challenge the status quo in neural network design and further enhance machine learning capabilities across diverse domains. 4.9 Applications of RNNs in time series analysis. Recurrent neural networks, RNNs, are a class of neural networks that are designed to recognize patterns in sequences of data, such as text, genomes, handwriting, or numerical time series data emanating from sensors, stock markets, and government agencies. Unlike feed-forward neural networks, RNNs possess a hidden state that can capture temporal information, which makes them particularly suited for time series analysis. Time series data, inherently sequential and characterized by its continuity over time, requires a specialized approach to identify the underlying trends, seasonality, and noise. RNNs serve this need by using their internal state memory to process all the elements of the sequence one by one while retaining the information. The architecture of RNNs, which folds the present with the past, allows for the persistence of information across inputs. In time series analysis, this characteristic of RNNs plays a pivotal role in predicting future values based on previously observed data points. When an RNN processes a time step, it combines the current input with its existing state, a representation of what it has learned so far, to produce an output and update its state. This iterative process continues through the sequence, enabling the RNN to make informed predictions about what comes next in the time series. One application of RNNs in time series analysis is in financial markets, where they can process sequences of price data to forecast future stock prices or to estimate the risk of potential investments. Financial time series are complex and noisy, with their patterns and causal relationships changing over time. RNNs are particularly adept at handling such non-stationary data by learning the dynamic temporal behaviors of the markets. Their ability to weigh recent data more heavily allows for adaptive model updating, which is essential in the volatile and ever-changing financial landscape. In weather forecasting, RNNs are used to model sequences of meteorological data over time. Weather data is highly temporal and often displays patterns that are difficult to capture with conventional statistical models. RNNs can take into account the sequential dependence of weather phenomena and predict future meteorological conditions such as rainfall, temperature, or wind speed. The coupling of historical weather patterns with current sensor data allows RNNs to extract complex features and provide accurate forecasts that can be used for planning and decision-making in agriculture, disaster management, and aviation. RNNs also find applications in the field of energy demand forecasting. As energy grids become smarter and more data-driven, the need for accurate demand forecasts is critical to ensure the efficient operation of these systems. Time series models based on RNNs can leverage historical consumption data to predict future energy needs. These predictions are essential for balancing supply and demand, scheduling power generation, and for planning the integration of renewable energy sources into the grid. In the healthcare sector, RNNs are used to analyze time series data obtained from wearables and medical devices to monitor patients' health and predict outcomes. For instance, heart rate monitors track a patient's cardiac activity over time, generating a time series that can be analyzed by an RNN to detect anomalies or trends that may indicate a health issue. In another example, RNNs can process sequences of laboratory test values to forecast the progression of a disease or the efficacy of a treatment. The sequential analysis of patient data can lead to more timely and personalized care interventions. The field of natural language processing, NLP, also employs RNNs for time series analysis, where the sequences are instead based on text data. A sentence is a time series of words, and RNNs have the ability to predict the likelihood of subsequent words in a sentence, which is essential for tasks such as machine translation, text generation, and speech recognition. By processing each word in context, RNNs capture the syntactic and semantic nuances of language, enabling an understanding that can be used to produce more coherent and contextually relevant text outputs. RNNs are instrumental in the domain of predictive maintenance, where they process time series data collected from machines and equipment to predict failures before they occur. Collecting and analyzing sensor data over time can reveal the machine's performance patterns and lead to early identification of potential problems. The predictive capabilities of RNNs help in scheduling maintenance activities proactively and avoiding costly unplanned downtimes. Further expanding the applications of RNNs in time series analysis, these networks have proven effective for analyzing sequences of biological data. In genomics, for instance, RNNs can process the sequential data of DNA to recognize patterns associated with certain diseases or traits. This sequence analysis can lead to advances in personalized medicine by identifying genetic markers of diseases and informing tailored treatment plans. In the retail and e-commerce industries, RNNs analyze customer behavior over time to create personalized experiences and improve inventory management. The sequential data of customer purchases and interactions can be analyzed to anticipate future buying behavior, tailoring marketing campaigns and product recommendations to individual preferences. Accurate forecasting using RNNs also supports inventory optimization by predicting demand surges and avoiding both overstocking and stockouts. The use of RNNs in time series analysis is not without challenges. One of the issues faced with this model is the vanishing gradient problem, which occurs when gradients calculated during the training process become too small for the network to learn from, hindering the learning of long-term dependencies. Variants of RNNs, such as long short-term memory networks, LSTMs, and gated recurrent units, GRUs, have been developed to mitigate this issue. These variants incorporate mechanisms that control the flow of information and can retain it over longer periods, making them more robust for modeling time series data that span vast time horizons. Despite these challenges, the flexibility and adaptability of RNNs make them one of the go-to models for analyzing and forecasting time series data across various domains. Their capacity to learn from sequence dependencies and to incorporate context into their predictions has made them invaluable in extracting meaningful insights from chronological data. As data continues to grow in volume and complexity, RNNs and their variants will undoubtedly remain crucial tools for time series analysis, leading to more effective decision-making and the advancement of numerous fields touched by this form of data. 4.10 Latest advancements in recurrent networks. Recurrent neural networks, RNNs, have undergone significant development since their inception. Early architectures were limited by short-term memory and were prone to issues such as vanishing and exploding gradients. However, as research has advanced, various techniques and innovations have been introduced to overcome these challenges. One of the first improvements was the creation of specialized RNN variants such as long short-term memory, LSTM networks, and gated recurrent units, GRUs, each with unique gating mechanisms to regulate the flow of information and maintain longer memory. Recent work in RNNs focuses on enhancing their ability to learn from data with complex temporal dependencies. Attention mechanisms, initially popularized within the context of sequence-to-sequence models in natural language processing tasks, have been incorporated into recurrent networks to allow them to focus selectively on different parts of the input sequence. This is particularly advantageous in tasks where certain pieces of information are more relevant than others for making predictions. By integrating attention, RNNs can weigh the inputs differently, substantially improving performance on a variety of sequence modeling tasks. Another advancement in RNNs is the incorporation of memory augmentation. Networks such as differentiable neural computers, DNCs, or neural Turing machines, NTMs, combine RNNs with external memory resources, vastly expanding their capacity to remember and manipulate data over extended sequences. These models use mechanisms inspired by the way traditional computers write to and read from memory, but with the flexibility and learning capabilities of neural networks. DNCs, for example, can learn to use their memory to solve complex tasks like graph traversal and reinforcement learning challenges, which were previously difficult for traditional RNNs. RNNs have also benefited from improvements in regularization techniques. Dropout, a regularization method often used in feed-forward neural networks, was adapted for RNNs through the introduction of variational dropout. This technique applies dropout to the recurrent connections and input units consistently across time steps, which helps in preventing overfitting and enables robust training of larger RNN models. Advanced regularization strategies have led to the ability to train deeper and more complex recurrent networks that have stronger generalization on unseen data. Meta-learning, or learning to learn, is another area that has seen RNN applications. RNNs are trained across a variety of tasks such that they can quickly adapt to new tasks with minimal additional training. This is particularly beneficial when dealing with a multitude of tasks that share underlying structure but differ in specifics. This approach has enabled the development of models that can be rapidly fine-tuned to new datasets or tasks, facilitating the creation of more versatile and adaptable machine learning systems. The integration of RNNs with reinforcement learning has provided another avenue for advancement. Recurrent models can be utilized to handle partial observability in reinforcement learning environments where an agent only has a limited view of the state space. By maintaining a memory of past actions and observations, RNNs help the agent infer the unobserved aspects of the environment, allowing for more effective decision-making. This powerful combination is being leveraged in domains such as robotics, where agents must operate in dynamic and unpredictable settings. Transfer learning has also been a significant aspect of RNN innovation. Here, a pre-trained network on a large dataset is used as a starting point for training on a smaller, possibly related dataset. This approach effectively leverages data from one domain to improve performance in another. Large-scale language models like GPT and BERT, though not based on traditional RNN architectures, demonstrate the potential of transfer learning in sequence models. Adapting similar principles to RNNs can lead to impressive performance gains in domain-specific tasks without the need for vast amounts of task-specific training data. Optimization algorithms specific to RNNs have seen improvements as well. Techniques such as truncated backpropagation through time offer a way to handle long sequences by backpropagating errors through a limited number of time steps, thus making model training more computationally feasible. This and other novel training techniques, such as the use of echo state networks, which require less training due to their large, fixed random hidden layer, have opened up new capabilities in the efficient training of RNNs. Furthermore, advances in hardware and distributed computing have greatly accelerated RNN training and inference. Specialized processing units like graphics processing units, GPUs, and tensor processing units, TPUs, provide the computational power necessary to train complex RNN models on large datasets within a reasonable time frame. Parallel processing and distributed training algorithms enable the scaling up of RNNs to unprecedented levels, thus facilitating the development of more sophisticated and powerful sequence modeling applications. Finally, interdisciplinary research has been key to the progress in RNNs. Insights from neuroscience, for example, have inspired the design of RNNs that more closely mimic the dynamics of the human brain. This biological plausibility not only aids in understanding how neural networks operate, but also potentially unlocks new functionalities and learning capabilities. By drawing from a diverse set of fields, researchers are able to foster innovative approaches that continue to push the boundaries of what RNNs can achieve.